Good morning. I'd like to talk to you today about some of the work that I've been doing on one of the most spectacular ecosystems on the planet, and this is coral reefs. When I first looked at them, like everyone else, I was overwhelmed initially with their biodiversity. But what made it easier for me is that I wasn't so much interested in what they were called, but what all the individual fishes and various organisms were doing, what their jobs were. And as a consequence, I realized that biodiversity is largely skin deep. So that we look at something like Nemo, and everyone likes this beast, but the reality is you only really like it because it's orange. If it was grey, you wouldn't be half as interested. And as a consequence, I wanted to look beyond colour and see what was really going on. So for me, I looked at all of these things as machines. So I look at a fish in terms of how it works as a machine and what it does on the reef. So I can go to a reef and I can see a fish skull from a long dead fish, and I can reconstruct in my mind's eye how it used to feed, what it used to do, and what its job was in terms of the system. And as a consequence, I can look at a single bone like this, and I can tell you how it fed, what it probably fed on, where it probably fed on it, and all those other details about it. So what does this mean? Well, it means I can tell you all sorts of fascinating tales about fish bones and how wonderful they are. But as with most things, there's a time and a place, and perhaps not every fish barbecue is the way to do it. But for me, I can't escape this. I'm always fascinated. This bone is really important. It's the premaxilla, it's the upper jawbone. And what it enables fishes to do is this. They can protrude. Now, you go, well, that's okay, but what's really good about this bone is that it tells you how much they can protrude. The longer the bone, the more protrusion you get from the fish. And this is wonderful because this basic set of rules can be applied to all sorts of fishes, not just living ones, but also long dead ones. So fossil fishes still have the same bones, so we can go back through time. And what this does is the ability to understand these bones gives us a new language. We can interpret both the current world and the past world in terms of form and function. So we go back and we look at how things were operating in the past. And what we see is that there's been a huge change in the ability of fishes to grab their prey. Now, you always assume that a fish can snap up its prey, but it's not been that way. 100 billion years ago, fishes couldn't snap up their prey and do the protrusion. They had to grab it as they shot past. So that ability to snap up prey is something that's evolved over the last 100 million years, and we see this progressive change in the heads of fishes and their ability to go and get things. There's a concomitant decrease in the size of their prey over this time. Basically, what's happened is if you're a prey item like a little crab, you've grown smaller because the crabs were so much more vulnerable. And today on coral reefs, the average size of a crustacean is less than 1 millimeter. You've got to be very, very small, and you've got to hide. If not, you just get snapped up. So this functional approach can be applied to anything. It's the same with things like teeth. For fishes, for about 300 million years, teeth have basically had one axis of variation. You can either be long and pointed and puncture flesh, or you can be on the other side and you can be more even and rounded and scrape things. So there's been, the scraping, pointing, stabbing, axis of variation and things in between. 25 million years ago, however, there was a new kind of tooth. And these long-toothed fishes started to feed in a completely different way. What they had is they've got these long teeth, and they're like having a whole row of toothbrushes in your mouth, and they brush the surface of the reef. And what they've done is they've changed the whole dynamic of reef feeding. It used to be that fishes ate invertebrates, and invertebrates eat the detritus on reef, this organic, rich dust. The fishes, using these new long teeth, were able to cut out the middleman, the invertebrates. So instead of the fishes feeding on the invertebrates, the fishes feed on the food of the invertebrates, and as a consequence, they get all of the nutrition. The biomass of these is huge, and their intensity of feedings fundamentally changed reef trophodynamics, and they probably led to the reefs that we see today. So it's a new way of looking at how reefs work, and as a consequence, we can reconstruct reefs from the Jurassic, the Cretaceous, Eocene to present as functional units. You can see how they developed and how the systems worked. All of this is based on an understanding of this functional approach. So the approach is useful not only for the past, but we can also look at the present. And we can talk about one of the big questions in coral reefs these days in terms of biodiversity. Why are there so many species on coral reefs, and how do we explain global variation in species richness? To address this, my colleagues and I went out and we quantified biodiversity. And if you look back 48 million years ago, most biodiversity was in what's now Europe. So if you want to look at the ancient fishes, you go to Italy. The corals, you go to southern England. For mollusks, you go to Paris. That's where all of the biodiversity was. But it moved through time. 5 million years ago, you'd find it just north of Australia in the Indo-Australian archipelago. And that's where it remains to this day. Now, in terms of why there's so much there, regardless of the complexity of our models and the approaches we take, what we find is there's one thing that comes out is always reef area. So why are there so many species on the Great Barrier Reef? It's because it's part of this largest concentration of reef area in the world. That's why we've got so many species. But the functional approach enables us to ask the really important question: does it matter? Does biodiversity actually convey any useful benefits for the system? Now, the assumption is the answer is yes, because if you've got lots of species, you've got lots of redundancy. In other words, if you lose a species, it can be replaced by another species. So the job keeps on going. So what we did is we wanted to look to see if this actually happens and if it works in that way. So what we have, this is a plot of the number of species in each of the potential jobs. So on the horizontal axis, these are kind of like all the jobs that you could possibly do on a reef for fishes. And the vertical axis is the number of species doing each one of those jobs. Now, what struck us immediately is that some jobs are extremely popular. So it's like all of the fishers decided, this is what I want to do. It's like being a professional Tim Tam taster. It's something you can't resist, you've got to do it. So that was kind of striking. We didn't realize it'd be so overrepresented. But what was even more striking and frightening is that you get the situation where a third of the species are single species entities. In other words, there's one species doing a specific job. If you lose that species, you lose that function, you lose that job, and there's no real replacement. So if you go to a system and you have these giant hump-headed parrotfishes, or you have the giant moray eel, and you lose those individuals, those species, there's going to be no replacement. So high diversity systems can be just as vulnerable as their low diversity counterparts. So biodiversity doesn't buy us the insurance that we once assumed. And it's not just the past and the present, but it's perhaps the future that's the most important. When we're looking at the future of coral reefs, this functional approach has enabled us to revolutionize our approach to management. So rather than looking at biodiversity to protect, we're now starting to look at resilience, that is to say, their ability to withstand change. As our American colleagues call it, the bounce-back ability of reefs. That's really important, and it's had global uptake. So this new approach has been welcomed around the world, and now we're seeing people trying to protect parrotfishes, not because of their biodiversity, because they're different species, but because of the functional role that they deliver in reef systems. They're important for the reef. Now, this is sorely needed because reefs around the world are being overwhelmed by the speed and the scale of environmental change. Now, I'm sure you're all aware of the latest bleaching that's been brilliantly documented by one of your fellows. And this is particularly concerning, but it's come on the back of major changes to the reef already. In the last 50 years, the modal coral cover on the Great Barrier Reef has gone down from about 40 to 50% to less than 10%. Reefs were already struggling. Bleaching now is on top of that. So we're having all sorts of issues. If you look on Orpheus Island, this is an inshore reef where I work, typical of the inshore reefs, it's suffering more than most other reefs. It's dealing with bleaching and it's dealing with the problems of sediment. The bottom line is that this island has had something like 3,700% increase in sediment loads. That's what it used to look like in the past. That's what it looks like today. That is a real issue. And the problem is that this is overwhelming natural processes. So it used to be that the fish would feed on this turf algae. That's the basic process of keeping the reef clean. But the parrotfishes have pretty much stopped feeding on the reef. The rabbitfishes have just about stopped completely. And what we're left with is this system where things are changing and there's this general decline. Now, the problem with this is that we've realized that our natural cleanup processes are our old friends, the long-toothed fishes. What they do when they're feeding is they brush all of the sediment off the reef, They then ingest it, they wrap it in mucus as they're processing it, and they deposit it in holes in the reef. So it's like having a Dyson vac at home that cleans up your house, puts it all in biodegradable sausage skins and hides it in your garden, which is great unless the neighbours find it and wonder what you've been doing. Anyway, but for reefs, that's just what they need. These fish clean up the reef about every 4 months. And on inshore reefs, these are even more important. These parrotfishers, they're cleaning up the reef crest every 27 days. So they're the natural reef cleanup department. The problem is they're now overwhelmed. So the good news is we've found that at a local scale, very small scale, we can get the processes starting again. It's like having a defibrillator for reefs. We can go in, short, sharp shock, we can get it going again, the fishes start feeding again, we can get processes operating. However, we've got to be careful. We've got to make sure that this is going to happen. So I'm optimistic that Great Barrier Reef will regenerate, but we've got to make sure that it does. And the extent to which it regenerates depends on our ability to keep the remaining reefs in good condition. That's going to be critical. So we've got to get water quality under control so that these fishes can go and do their job. So for the future of coral reefs, what's going to be important is understanding which are the real fishes that we need to watch out for and which aren't. So our old friend here, Nemo, he's beautiful, I'll give you that, but functionally he's irrelevant. He's about as much use as a bedbug, something you want to look at, but you don't necessarily want to have around. The real heroes on the reef are these guys. They're grey, they're boring, but they're the ones that are going to keep reefs in good condition. So we've got to look after them. We've got to work with them. If we work with them, we help them, we protect them, and we change the environment for them, they will keep the reefs clean and give us a clear and bright future. Thank you very much.
Thank you, David.
No worries.
Any questions for David? I've been wondering about this mouthful of toothbrushes, but I just suddenly realized that this is going to be quite helpful as a Tim Tam taster.
Yes, you can suck the chocolate off first and then go to the crunchy bit.
A question, yes.
You said there were a lot of species doing the same job, but is that just our misunderstanding of what they're doing? Because you would think that one of them would outcompete the others if they were all filling exactly the same niche.
That's what's always been assumed, and all of the evidence we've got, most of the evidence for that comes from molecular work, but it seems that biodiversity is being maintained largely through biogeographic events. So there's lots of divisions, reconfigurations, so that the old competition and that kind of control of species richness doesn't seem to apply. So we can explain the number of species largely by looking at history. Most of the biodiversity on the barrier reef is about 2 million years old. So biodiversity as we know it is a relatively recent phenomenon that's just come on the scene.
Here, yes?
Over here.
Up the back first.
So,
Sorry, sir.
one gets so much depressing news about reefs being destroyed. Are there examples where reefs have been regenerated on a large scale, and how was that done?
Reefs are continually regenerating, so we've had several bleaching events and reefs have come back. The one we've just had is the largest of its type, the scale, 900 kilometers of reef with massive bleaching. It's the frequency that's the problem, the extent and the scale of it. The thing is with reefs, they've got amazing regenerative capacities. It's not like working with pandas where it's a species that doesn't seem to want to feed or breed. Reefs really seem to want to help themselves. It's just that we've got to put the effort in and make sure the water quality is there, and we've got to get on top of climate. We've got to change the way we're dealing with fossil fuels. It's a major problem.
One last question.
Following on the same theme, it wasn't clear to me from the end of your talk what you're specifically proposing to help the coral grinding fish.
The bottom line is what you've got to do is get rid of the sediments temporarily. These sediments lock in it's like a phase shift. They go to a new condition, they're locked in and they can't get out. What you need is a shock to change the system. Once you get it moving out, the fishes will move in and maintain it and try and help it. It's just a case of once you get the systems locked in, it's very, very hard to wait for them to naturally recover. You've got to take some intervention. Yes, well, what we've been using is airlifts at this point in time.
Thank you very much, David.
Thank you.